Good afternoon, everyone. This is Advanced Thermodynamics and Combustion course being conducted by NPTEL. Being conducted by IIT Guwahati under the NPTEL program. And this is the ninth live tutorial session of this course. The theme for today's discussion and questions will be kinetics, which is the theme of your week nine's contents for this course. And instructor for the course is Professor Niranjan Sahu, affiliated as professor with the Department of Mechanical Engineering, IIT Guwahati. And my name is Aditya Sharma, and I'm the teaching assistant for these tutorial sessions. Also, I'm a research scholar at the Department of Mechanical Engineering, IIT Guwahati. So we shall start this session in another couple of minutes. So let's wait, and then we can start the session. Thank you. So I believe we can start with the session. So the theme is chemical kinetics. So what is chemical kinetics? Chemical kinetics basically is the science which deals with the rate. Rate of what? Rate of chemical reactions. Okay. So this is your basic. This is the basic idea about what chemical kinetics is, right? The structure of the session will remain as it is. First, we will be briefly discussing the topics that have been covered in week 9. After that, we will have some conceptual questions. After that, we will be having numerical questions, and then we will conclude the session. And after 1 hour of the session, we will take a 5 minutes break. Okay. So, all right. So let's discuss the topics first. So there are total 3 lectures uh, in week 9, lecture 23 to lecture 25. So first topic in lectures the lecture 23 is rudiments of mass transfer. Okay. So in this whole week, what we are trying to do is we are trying to study the chemical reaction that takes place during combustion, right? Because the uh, course name is Advanced Thermodynamics and Combustion, right? From the perspective of combustion, we need to see things, right? Whatever we are discussing, we need to see it from that perspective only, right? All right. So what I was saying that we have to see our discussions from the perspective of combustion in whatever topic we are discussing in these tutorials, right? So at present, I'm discussing the topics. Briefly, I'll discuss the topics. After that, we will move on to the conceptual questions and the numerical questions that will help you solve your assignments, right? Okay, so I was discussing this first heading, the rudiments of mass transfer. So before that, what I was saying is that the whole theme of this week's discussion revolves around understanding your chemical reactions in detail. Right? So for that purpose, we define our reactions as global reactions and then elementary reactions, right? And in elementary reactions, also based on the number of reactants, right? We define our reaction. For example, it can be unimolecular, right? Or it can be bimolecular, right? So this way we have done our discussion on the chemical reactions, right? So in this effort, the first topic here is rudiments of mass transfer. So this topic basically is from the idea of your diffusion. So if you have mm, more two or more than two species, right, in a mixture. and when they diffuse. Yes, 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 Nehal, you can ask the question. You can also switch on your mic if your mic is working.
Hello, sir.
Yes, yes, Nehal, you are audible.
हिंदी comfortable?
Yes.
सर मैंने वो कोर्स की वो एग्जाम फीस का वो नहीं भरा है, उसकी डेट चली गई है।
Okay.
तो
So that Nehal cannot be helped because there was a deadline for that. Also, it's a 12-week course, right? But वो तो हो गया है, I believe. उसको तो maybe you can write an email to the NPTEL.
ओके सर।
Yes, that way if it works because it will be a special case in that scenario. Otherwise, I don't know. Like I haven't come across any such case where after the passing of this exam registration date,
ओके सर,
somebody
थैंक यू।
asks. Yes. So you will have to write an email to the NPTEL, and from there you'll get the correct answer. Okay.
ओके सर।
All right. So I was discussing the mass transfer and diffusion, right? So in this, from the perspective of mixing of different species, right? So for example, in combustion, if we have reactants, two reactants, right? Maybe fuel and oxidizer. So when they diffuse with each other, so in that case, when we have to do the analysis in detail, right? So how can we do that? So from that perspective, this topic has been discussed in this lecture, right? So in this topic, we come across our Fick's law of diffusion, right? So maybe I'll write Fick's law of diffusion. Just give me a second. Okay, so I'll write this expression for Fick's law. Uh, but Nehal, one thing what you can do is you can write your email in the chat box, right? In case I am able to contact the NPTEL team and clear your query, I can revert you back on your email if that is fine.
ओके सर, थैंक यू।
Yes. But you also write an email to NPTEL team. But from my side, I'll also try to see your case. Okay. So This is your fixed law, right? So if we have two species, let's say species uh, A and B, so rate of this mass flux of species, right, per unit area. So this is how we write it. I'll just write for A for one species, and for the second, it's kind of same. So this is your mass fraction. This is your mass fraction of A, right? Okay. And this is your diffusivity. dB is your binary diffusivity. Why we are calling it binary? Because two species are involved in it. Okay. Y is your mass fraction, then D is your diffusivity. Rho is your density of mixture. Okay. So this is your expression for mass flux of species A per unit area. Mass flux of A per unit area. Okay. Right. And this whole term, if you see, this is your this is called your diffusional flux. After that, this is a fixed law diffusion. Okay. After that, the next heading in this lecture is your global reaction. So, global reaction is nothing but the simple form of reaction, right? When we write some reaction, right? In that case, we write the initial reactants and we write the final products. Okay, so this is the simplest way to write a reaction. So this form of writing the reaction is your global reaction. Right? So different aspects of global reaction have been discussed in this topic, right? One such is what is the order of a global reaction, which is basically the exponents of your oxidizer and fuel, right? So let's say the exponent of your oxidizer is N, right? And for your fuel, it's M, right? So the order will be M plus M for this global reaction in that case, right? So this is your global reaction. Then the most important topic in this week's content is the discussion on elementary reactions, right? So, what are elementary reactions? So, whenever a reaction takes place, it is not the case that your reactants by some chemical reaction are directly jumping onto the products that you see on the right hand side of the global reaction, right? In between the reactants and products, there are intermediate states and intermediate reactions also. Okay, so there are steps of reactions, chemical reactions that take place in between the your reactants and final products. So these are called your elementary reactions, right? So comprehensive discussion has been done on elementary reactions. Okay. So elementary reactions can be unimolecular, as I was saying earlier. So it can be unimolecular, bimolecular, or thermolecular, right? So they will have the number of species they will have will be 1, 2, and 3 respectively in these cases, right? And then after that, in elementary reaction, we see what is this Arrhenius equation, right? So through your Arrhenius equation, what you do is you define the rate coefficient for uh, a particular reaction, right? So this is your Arrhenius. Because the rates also define the state at which your chemical reaction uh, is at the time when you are analyzing a particular reaction, right? So if I take one bimolecular reaction, right? So in that case, the consumption of this A reactant with respect to time, it can be given this way. Okay, where K is your rate coefficient. But then the rate coefficient, what we can do through your Arrhenius equation. Sorry, I have written reaction. It will be equation. So using this Arrhenius equation, you can define the rate coefficient. Okay. So rate coefficient can be written this way. Okay. Where A and B are your constants, right? And E is your activation energy, T is your temperature, R is your universal gas constant, right? So this is your Arrhenius equation. Okay. After that, if you see the next topic, this is your rate coefficients and equilibrium constants. So I'll just quickly brief it. So here also there is discussion on uh, rate coefficients of your reaction, right? Which is your K, like I have discussed previously. So This is your rate coefficient. Right. Alright. So in case your reaction is in equilibrium, right? In that case, how do we define our this equilibrium constant? So this has been discussed in this topic, or by means of a bimolecular reaction. This has been discussed. So how the rate constant of a forward reaction and the rate constant of a reverse reaction, right? How they can contribute to the equilibrium constant. So all this discussion has been done. Also, a point is to be noted in this case that your equilibrium constant can also be expressed in terms of your partial pressure. So this discussion has been done under this topic. After that, the next lecture is your lecture number 24, where in the first heading, this from the previous lecture, the discussion of global and elementary reactions. So it's a recap of all that discussion in this heading of this lecture. Then the next heading is your steady state of approximation. So basically, what this topic suggests is that in your reactions, uh, some steps you can consider as your state reactions, right? So, what is the idea of such supposition is that it uh, simplifies the analysis of your reaction, right? So this is your steady state approximation. Okay. So this has been discussed by means of your Zendovich mechanism, right? Which is for nitric oxide. So this is your steady state approximation. After that is uh, the topic unimolecular reaction mechanism, right? So, so in this discussion, one important thing that is to be remembered is this your energized molecule that you get, right? So in between this your unimolecular molecular reaction, you get some energized state, right? So if you see your lecture slides, it has been denoted by a star, superscript star, right? So how this affects your whole reaction. So all this has been discussed, and how eventually it helps to it leads to your products, this energized molecule. So this has been discussed in this particular heading, right? So it shows that in the first step, what we get is from A, we get this energized molecule, right? And this energized molecule has in two ways it can proceed, right? One of which is that it directly gets converted into your product, okay? And then rates linked to this unimolecular uh, reaction is also discussed under this topic, okay? After that is your chain and chain branching reactions. So the significance of this chain reactions and chain branching reaction is that uh, these reactions are encountered in places where we have explosions, right? Or reactions that are explosive in nature. Such reactions encounter the chain reactions or chain branching reactions. So, if you see a case of your flame that is self-propagating, right? So, the self-propagation of the flame is made possible by your chain branching reactions, right? So chain branching is that uh, in the reaction, let's say we have some step which leads to a radical, right? So radical is highly reactive. So this radical will further have reaction with your some species, right? Which will again give rise to some radical which is highly reactive, right? So this way your chain keeps on moving, right? That's why called a chain reaction. Okay, so right. So then there are discussions. Then there is this how this chain initiation takes place and how the propagation of this chain takes place, right? And eventually how the chain terminates. So all this has been discussed under this topic, right? And then the next topic is your chemical time scales. So time scales when we are studying the chemical reactions or the rate of chemical reactions is very important, right? Because it enhances the analysis of our study. So when we are studying some mixture and some reaction, so from the perspective of your mixing also, right? So there is some time scale related to mixing. So comparing that with the uh, time scales of your reaction enhances the analysis of your whole reaction that you're studying. So from that perspective, the chemical time scales have been discussed, right? And then the expression for your characteristic chemical time. So all this has been given in your this heading chemical time scales. Okay. So the time scale for your bimolecular reaction is also given. Firstly, the discussion is based on your unimolecular reaction, and then there is discussion on bimolecular reaction also. So expressions have been given in detail in your slides, right? Okay. Then moving on to the next topic, that is your partial equilibrium. So it states that in your whole, if you see your whole combustion process, so there are reactions for a particular combustion process, right? For a combustion of a particular fuel, there are intermediate reactions that are fast, and there are intermediate reactions that are slow, right? And the fast reactions encompass your reactions like chain propagating reaction and chain branching reactions, right? And for the purpose of simplification of the analysis, what we do is we say that this your fast reactions are in your equilibrium state, and then our focus then moves on to the slow reactions only, right? So this simplifies the study of the whole combustion process, right? In that case, the partial equilibrium of the whole process is has been called this partial equilibrium of the combustion process, right? So in some part, this whole process is in equilibrium, so that has eventually been called the partial equilibrium. So this is your partial equilibrium from lecture number 24. Okay. Then is your final lecture of this week's. That is week number 9 and lecture number 25. So now in this lecture, what has been done is that we have taken examples, and by means of examples, the whole discussion has been the discussion that has been done on chemical kinetics has been consolidated. So few examples have been taken, right? Like the first example is of hydrogen oxygen reaction system. Okay, then is your carbon monoxide oxidation. Then is your formation of nitric oxide or oxides of nitrogen formation. And then in the conclusion of this lecture, this oxidation of fuels also has been discussed, right? So the lecture starts with the global and elementary reactions, the revision of global and elementary reactions that we have discussed in the past two lectures, previous two lectures. Okay, so the rate of fuel of consumption, right? And what is a unimolecular, bimolecular, molecular reaction? So this has been discussed in this your 25.1. Then is your equilibrium products of combustion. Okay, so when your reaction is in equilibrium, what are the products that we get to see? Okay, so two cases have been presented. One is of lean mixture and one is of rich mixture. Okay, so what is a lean mixture? What is a rich mixture? We have discussed in the previous sessions. So in the lectures, in this lecture, the case of propane and air mixture has been taken. So propane is being combusted in the presence of air. So what different products we get have been given, right? After that, what has been done is after that the lecture moves on to your hydrogen oxygen reaction system. So why this discussion has been brought into this lecture is that it is important from the perspective of your rocket propulsion. Okay, so the fuels used in rocket propulsion is one of the fuels that is used in rocket propulsion. So that is why it becomes of importance. Okay. So the whole detailed discussion of your hydrogen oxygen reaction system has been given, right? And then a very important pressure versus temperature graph also has been given. Okay. So I'll just draw this. This. So this is your H2O2 reaction system. Yes. So what is given is a graph something like this. Here we have pressure and here we have temperature. And your graph looks something like this. So this line has been called your first limit. This is your second limit. This is your third limit. Okay. So these pressure and temperature values are those values which are of the initial conditions. These are the initial conditions of your explosive or charge that you will be using for your explosion, right? And this graph suggests that if your pressure and time coordinate falls in this region, right? In this region, in that case, your explosion won't take place, right? But if it falls in this region, in that case, explosion will take place, right? Then for this case, again, there will be no explosion, and for this case, again, there will be explosion. Okay. So this is the graph that has been shown in your H2O2 reaction system. And what attracts such behavior? So for all the regions, a detailed discussion has been done under this topic, right? After that is your very brief discussion on carbon monoxide oxygen, right? Which eventually gives to carbon dioxide. Okay, the oxidation of carbon monoxide leads to carbon dioxide. So intermediate reactions, the chain branching reaction and the chain propagation reaction, all this has been covered in this heading. After that is your oxides of nitrogen formation. So in this oxides of nitrogen formation, so in this discussion it has been said that when a combustion of a hydrocarbon takes place, so nitric oxide is formed, right? And three mechanisms have been mentioned by which this nitric oxide gets formed, right? So Out of those three, first is your Zeldovic mechanism. Second is your Fenimore mechanism, which is also called prompt mechanism. And the third is your intermediate mechanism. Okay. So Zeldovic mechanism uh, is used when the temperatures are greater than 1800 Kelvin, right? So this is your Zeldovic mechanism. Then is your prompt mechanism or Fenimore mechanism. So when the mixture of your fuel and oxidizer, for that if the equivalence ratio, that is denoted by phi. So if your phi is less than 1.2, okay, so this is a rich mixture. In that case, prompt mechanism or Fenimore mechanism comes into picture as far as the nitric oxide formation is concerned. Okay. Then is your intermediate mechanism. So for intermediate mechanism, the phi is less than 0.8. So this is a lean mixture. So these three mechanisms have been discussed under the oxides of nitrogen formation. After that, the last heading of this week's lectures is oxidation of fuels. So three steps have been defined. So when the oxidation of a particular alkane, right, that is CnH2n, H2n plus 2. So three steps have been defined. So first is in the first step, your fuel is attacked by your radicals, right? After that, your intermediates oxide to form carbon monoxide and water. Okay. So first you get intermediate forms when the radicals react with your fuel, right? And then these intermediate forms are oxidized, okay, to get your carbon monoxide and water. And then in the third stage, your carbon monoxide and hydrogen are oxidized to eventually obtain carbon dioxide and water. So these are the three steps that have been mentioned when the oxidation of a fuel takes place. Okay. So how complex a reaction can be, right? The idea of this has been given by means of an example intersection. So this says that methane, the example of methane has been given, right? So the mechanism of methane oxidation consists of 277 elementary steps, involving 49 species with average residence time of 0.1 second for species. Right? So you can take the idea from this information that 277 elementary steps are involved in the oxidation of methane, and the intermediate species that we see, right, or the total species that we see in the whole oxidation mechanism of methane are 49. The number is 49 species, right? So the grandeur of the whole combustion process or oxidation process, you can imagine. Right? So this was your lecture 25. Right. After that, now we'll move on to the questions. Okay. Pretty straightforward questions. You can try to answer these questions. Okay, so your first question is on rudiments of mass transfer from your lectures, and it says that the mass transfer rate law for reacting gas mixtures is governed by the fixed law of diffusion. So whether this statement is correct or not. So when we discuss the fixed law of diffusion, so this the discussion is limited to only non-reacting gas mixtures. Okay. So the diffusion, when we are trying to analyze using fixed law of diffusion, in that case, your diffusing elements or species have to be non-reacting. In case it's reacting, the fixed law of diffusion won't be applicable. Okay. So because it says for reacting gas mixtures, so this becomes a false statement. After that, the second question again is on rudiments of mass transfer. So it's a multiple choice question, multiple choice type of question. So there are ways by which your mass transfer takes place. Okay. So Nehal is saying velocity of the flow. So okay. So what I was saying is that there are ways by which your mass transfer takes place. One way is that there is a difference in the concentrations of the two elements or two or more elements that are diffusing with each other. Right? But then there is another case or another method that is by means of turbulence. Okay. By means of turbulence, also the mass transfer takes place. Okay. And in that case, what governs the mass transfer is obviously your velocity of the flow, right? But what happens in turbulent flows is that uh, we see eddies, right? Eddies are somewhat like circulations, right? So such eddies of different scales, right? Of different sizes, we see in turbulent flows. So if you will take some course on turbulence or turbulent flows, so this will be discussed there in detail. But for this particular course discussion, we will limit it to this much information only, that in turbulent flows we encounter eddies, right? And the scale of these eddies also affects the mass transfer, right, in a particular flow. So B option, sorry, in that case is also correct, right? This should have been B here. By mistake, I have written C, right? In that case, these both A and B options will be correct, right? So correct answer to this question, though not given initially, not given in the choices, given choices, but it will be in the present. If we see the present state, it will be option C. Okay, all right. So, so before moving on to the next question, we'll just take a short break for 5 minutes. After that, we will continue with the remaining part of the session. Okay, so we can start with the remaining part of the session. So the next question is based on your fixed law of diffusion, and it states that the mass conservation requires that the sum of diffusion fluxes of the species in a non-reacting gas mixture should be zero. So whether this statement is correct or not, they can try to answer this. We can try to answer this whether this statement is correct or not. So this is the mass conservation, then sum of diffusion fluxes or diffusional fluxes of the species involved in the non-reacting gas mixture should be zero. So because it's a non-reacting gas mixture, so fixed law of diffusion we can use in it. Okay. Then it says that sum of diffusional fluxes. So we know that the sum of diffusional fluxes for the species which are taking part in the diffusion in a non-reacting gas mixture. So the sum is zero. So this is a correct statement. Okay, option A is correct. Then the next question is on fixed law of diffusion. We can try to answer this. Yes, of the unit of binary diffusion. The unit of binary diffusion is meter square per second. Okay, C option. Straightforward. Then moving on to next question. So what is binary diffusion? This here is binary diffusion in the Fick's law. D subscript AB. Okay, for this particular case. But yes, this is a binary diffusion. So question number 5 then. This is on global and elementary reactions. So it states that an elementary reaction has only two reactants, while a global reaction can have more than two. So whether this is a true statement or a false statement. Okay, so the answer to this question is false. Why so? Because we have seen in our discussion on the topics of this week's content that the elementary reactions can be unimolecular, they can be bimolecular, and they can be termolecular. That is three reactants of species in that case. Okay, so in that case, this becomes a false statement. Okay. Then moving on to the next question, that is question number 6. The question is on elementary reaction. So I've just mentioned that the intermolecular reactions involve three reactant species. And what will be the order of these reactions? The order will be third order. Okay. So if you see your options, your C option is the correct answer to this question. So let's see the next question. Yes, this is on elementary reaction, question number 7. We can try to answer this question. The question is on the reaction order. Please read the statement and then whether the statement is a correct statement or a false statement. You can try to answer this. Okay. So for your global reactions, the order can be, it is not a compulsion that order has to be an integer, right? It can be a decimal in decimal also. But for your elementary reactions, the reaction order is always an integer. Okay. So in that case, this is it. positive. Moving on to next question then. Question number 8 on rate coefficients and equilibrium constants. Yes, please read the question and try to answer this. The question basically is on the equilibrium condition that we see in an elementary reaction. Okay, so if you know the way in which we define the equilibrium condition, then you will be able to answer this question. So please see this. Okay, so the first option here is the rate of change of concentration for the reactant species must be zero. The first option says that. The question is in an elementary reaction at equilibrium constant, the dash must be zero. Okay. So first option is the rate of change of concentration of reactant species must be zero. Then the second option states that the time rate of change of concentration of product species. So the second option states that it's just not the rate of change of concentration, but this rate of change is with respect to time, and that too not for reactants, that for product species. The third option states that the rate of change of concentration for all the species must be zero, while the last option states that the time rate of change of concentration for all the species. So it states that yes, it's the rate of change of concentration of all the species, but with respect to time. Okay. So out of these four options, so because in an elementary reaction, when an equilibrium takes place, the concentration on both sides of the reaction, in the reactant side and also in the product side, in both the sides, the concentration rate of change of concentration with time is zero. Okay, so the option fourth, D option will be correct for this question. Okay, so this was your question number 8. Now we will see question number 9, which again is on rate coefficients and equilibrium constants. So in lecture number 23, the last topic of lecture number 23, this is from there only. So please first read the question and then answer that whether this statement is a correct statement or it's a false statement. So let's discuss this question. So question number 9. Let's say we have a biomolecular reaction which is A plus B gives rise to C plus D, that case, the rate of consumption, time rate of consumption of your A, or it can be fuel, is given this way. So the equilibrium constant based on concentration, which is defined by Kc, can be given by this ratio, which is this. Okay. But I had previously mentioned that using the partial pressures also it can be defined. So let's see how we can define the equilibrium constant using partial pressures. Okay. So this is your PD. So this way your equilibrium constant on the basis of concentration of different species can be done, and based on partial pressures also it can be done. But for bimolecular reaction, the thing is that Kc is equals to Kp. Okay. Where A, B, C, D, A, B, C, and D are stoichiometric constants. All right. So this is the case for bimolecular reactions. Now, if you see a question for a bimolecular reaction, equilibrium constant based on concentration is not equal to equilibrium constant based on concentration. That is not the case. Okay, that is a false statement because it is equal. Right. So then moving on to the next question. So in the discussion on steady state approximations that we do in the discussion of elementary reactions, in the study of elementary reactions, uh, it was explained using a mechanism which is popular by the name Zeldovic uh, mechanism. Okay, so there is a statement. So it's a multiple choice type of question. So question states that this is question number 10. It states that Zeldovic or Zeldovich. Zeldovich mechanism defines the formation of, so which of these four is defined using the Zeldovich mechanism? Now it will be easy to answer this question. So Zeldovich mechanism is used to define the formation of nitric oxide. Okay, B option. In lecture 25, this mechanism has been covered in detail. So you may refer to lecture 25 if you wish to know about this mechanism in detail. So B option is correct for this question, question number 10. So let's move on to the next question. The question is on global and elementary reactions, the broad properties. And the question states that gas reactions are responsible for a flame being self-propagating. So the self-propagating flames are self-propagating by virtue of what type of reactions? Whether it's an elementary reaction, whether it's a global reaction, whether it's a unimolecular reaction, or whether it's a chain branching reaction. So the correct answer to this question is option number D. The chain branching reactions are the one which are responsible for the self-propagation of flames. So we have seen in the discussion of chain and chain branching reactions discussion that in such type of reactions we see radicals that are highly reactive. So once we have a radical, this radical again will lead to a reaction, and this new reaction will again give rise to radicals that will again continue this chain of production of radicals and then the reaction of these radicals further. Okay. So in branching, what happens is that let's say we have two radicals. So out of that, one radical will take part in the reaction further, right? It will the whole reaction will branch out from this particular radical. Okay, so that's why chain branch. So such type of reactions are seen in the self-propagating flames. So option D is correct for this question. Next, so this is your question number 11. Next question then is question number 12 on chemical time scales. So please read this question and see which is the correct option out of the four given options. Question is on time scale. It states that in a unimolecular reaction, the characteristic chemical time is the time required for the species to fall from its initial value to a value equal to dash times the initial value. So when a particular species falls in a unimolecular reaction from its initial value or concentration to a particular value, in that case we call this as the time taken for the species to uh, reach that value. is called the characteristic chemical time. Okay, so this value that is eventually reached by the species after the reaction is dash times the is somehow the multiple of the initial value, in a way multiple of the initial value, and what that multiple is, we have to answer this. The four options are given. A option is 2 by 3, B option is 1 by 3, C option is 1 by 7, and D option is 1 by E. Okay. E here is the Euler's number. So the correct answer to this question is option number D. Okay. It is the final value when the final value is 1 by E times the initial value. In that case, the time that this species has taken to reach this value is known as the characteristic chemical time. Okay, so this is your question number 12. Then next question is question number 13. It states that the prompt mechanism of nitric oxide formation is the one in which the mixture is lean, the mixture is rich, the mixture is at temperature less than 1800 Kelvin, the mixture is at a temperature greater than 1800 Kelvin. So three mechanisms we have studied in lecture 25 on the formation of nitric oxide, out of which first was the Lovick mechanism, which was which comes into picture when the temperature is well above 1800 Kelvin. Okay. Then second is your Fenimore mechanism, which is also known as prompt mechanism, which has been asked in the question. So for prompt mechanism comes into picture when your mixture is rich, right? So if you see the options, option B is the one which corresponds to the fill in the blank. Okay, so this is the answer to this question. And then third was your intermediate mechanism, N2O intermediate mechanism, which was seen in case of lean mixtures. So the option is correct. And these were your conceptual questions. Now we will see two numerical questions. So let's see numerical numerical questions now. This is 10 raised to the minus 10 and this is meter square per second. This is meter cube. Okay. So the question is on rudiments of mass transfer. The question states that we have carbon dioxide stored in a vessel. It is sealed with some rubber plug which has this diameter and this thickness. So what will be the mass loss from the vessel through the rubber plug? From the vessel through the rubber plug. So density of carbon dioxide is given this. Density is given, then binary diffusion coefficient, binary diffusivity is given. So let's solve this. So as per your Fick's law, this is the formula. Question number 14. Rate of mass diffusion is equals to DAB, then area of cross section, then density initially, density at the end, and this. Now DAB is given to us, area we have to find, row A1 is given, row A2 we will consider 0. Okay, so let's find, let's first write what has been given to us. This has been given to us 1.3 into 10 to the minus 10 meter square per second. Row A1 equals to 7.6 kg per meter cube equals to 0. Sorry, here is thickness. Not time. If I have by mistake called it, then this is thickness. The thickness is 30 mm, that is 0.03 meter. Then area equals to pi by 4 diameter square. So pi by 4, your diameter is 40 mm, that is this. So if you calculate this, this will come out to be this. So now using these all these values, rate of diffusion. So this. So this will be that is 2.11 into 10 raised to power minus 11 kg per second. That is 1.29 grams per year. Okay, 1.29 is the answer to this question. So this was a question number 15 and last question of the session. What is the value of x plus y? P3H8 plus XO2 plus PO2 plus H2O. Okay. So y will be equal to 4 and then for H8 equals to 2y implies y equals to 4. For oxygen 2x equals to 3 into 2 from carbon dioxide plus y into 1 from H2O implies 2x equals to 6 plus 4 because y equals to 4 implies x equals to 10 divided by 2 equals to 5. Hence x plus y equals to y plus 4 equals to 9. So this is your answer. 9 is the answer to this question. Okay, so this way we have come to the end of this session. Now I will conclude the session quickly. So we firstly discuss the topics covered in lecture 23, 24, and 25. Initially, the mass transfer and diffusion topic was discussed in lecture 23, and then global and elementary reactions were introduced in this lecture. After that, in lecture 24, uh, unimolecular reactions were discussed, and chain and chain branching reactions were also discussed in this topic. So these were the two main headings that were discussed in this topic. Headings that were discussed in this lecture. After that, in lecture 25, uh, uh, different reactions were discussed. One such reaction was S2O2 reaction. Okay, and from the perspective of its explosive nature. So all this was covered in detail. After that, oxides of nitrogen were discussed. Okay, in oxides of nitrogen, particularly nitric oxide, and the three mechanisms related to it were discussed. Right. After that, also the oxidation of carbon monoxide was discussed in this lecture 25. And at the end, in general, uh, the oxidation of fuels was discussed, and three steps were mentioned of that oxidation. Okay, so this was your topics, and after the topics, we moved on to conceptual questions, where we saw 13 conceptual questions based on these topics only. And from conceptual questions, we moved on to the numerical questions, where we discussed two numerical questions. One was on its law of diffusion, and then the second one was on stoichiometry. And this way we completed our session. Right? So I thank you for joining this session, and the next session will be on coming Sunday with the same timing. The timing will be 3 to 5 p.m. And thank you for joining this session, and happy learning, and let's see you in the next session. Thank you.